Hello everyone, I'm Lingling Wang from Huaqiao University, China. It's an honor for me to have this opportunity to present here. Today, I hope to introduce my ongoing research on crack and debonding of intumescent coatings and their effects on temperature development of steel elements. In today's talk, I will cover 4 parts: introduction, experimental program, test results, and conclusions. Compared to other types of fiberglass materials, intumescent coating have become the preferred option because of their merits such as attractive appearance, lightweight, and offset application. Despite widespread use, many gaps exist in understanding of fiberglass properties. Although progress has been achieved on the evaluation of thermal properties and durability, bonding with a protected substrate and the effects of their failure on steel temperature and structural fire resistance have not been investigated. In the specification, it is assumed that the intumescent coating char remains with and provides a uniform fire protection. However, cracking, debonding, and sometimes falling off are expected to happen because of the property mismatch between the coating and the steel. Under these conditions, a non-uniform temperature distribution will occur in the protected steel substrate, and the behavior and failure modes of steel structure may change consequently. A few studies have been carried out on the bonding properties of intumescent coatings. However, these studies have focused on modifying formulations to enhance the adhesive strength at ambient temperature. Engineers need to evaluate whether cracking, debonding, and detachment will occur during fire exposure and the effects of this failure on fire present functions. To investigate this problem, 11 specimens were tested according to the mechanical loading conditions and substrate geometry. That is, 3 unloaded plate specimens, 4 unloaded column specimens, and 4 loaded column specimens. An epoxy zinc phosphate primer was used on the surface of specimens before applying a solvent-based intumescent coating. The steel plates were protected by a primer and an intumescent coating on all sides. 3 thermocouples were embedded in each steel plate at the mid-thickness. The 4 unloaded column specimens consist of 2 duplicate I-shaped specimens and 2 duplicate T-shaped specimens. These specimens had primer and intumescent coating on all sides except the top and the bottom, which were protected by a 100 mm thick rock wall. Temperatures were measured at 2 locations along the column height and with 6 thermocouples at each location. Loaded column specimens consist of 3 I-shaped specimens and 1 T-shaped specimen. 1 loaded column used stainless steel, the other 3 used low-carbon steel. 1 of the 2 I-shaped carbon steel column was sandblasted before applying a primer. 1 test specimen had 1 layer of carbon fiber cloth placed on the surface after the application of the primer but before application of intumescent coating. The total height of the column was 2,750 millimeters. The exposure height of the column was 2,095 millimeters. Temperatures were measured at 5 sections along the column height, and each section had 6 thermocouples. The plate specimens were tested together and were hung vertically on steel beams inside furnace. Each unloaded column specimen was placed on a block of concrete inside furnace. The 4 loaded column specimens were pin-ended, and a compressing load was applied at the center of the cross-section. Before fire testing, each column was actually loaded to reach a load ratio of 30%, and the mechanical loading condition was maintained during the fire test. In all tests, the furnace temperature was regulated according to the ISO 834 standard temperature-time relationship. The actual deformation and temperature were measured and recorded continuously. Fire tests on loaded specimens were terminated when the actual deformation or deformation rate reached their limits. Fire tests on unloaded test specimens continued until the average steel temperature reached 700 degrees centigrade. With increasing temperature, intumescent coatings underwent melting, expansion, char formation, and char degradation. During melting stage, intumescent coatings had a relatively high fluidity, which enabled the coating to deform with the substrate. After entering the stage of expansion and solidification, the viscosity of the coating increases, and there is a strain mismatch between the coating and the steel, which may lead to cracking and debonding of the coating. This figure shows cracks of intumescent char on plate specimens during fire exposure. After fire test, cracking of intumescent char was observed for all specimens. According to crack size, cracks can be classified into 4 categories. These figures show failure of intumescent char for plate specimens and loaded column specimens and loaded column specimens respectively. Only type 1 and type 2 cracks were observed in unloaded specimens. For loaded column specimens, more serious failure occurred. These figures compare failure of intumescent char for loaded column specimens. Individual treatment has effects on failure modes of intumescent char. For example, compared to specimens without sandblasting, sandblasted specimen had larger and more cracks but less extensive detachment, thus less debonding. During fire test, its loaded column initially expanded and then shortened due to the rapid loss of steel strength. A column buckling occurred immediately after the shortening of steel column. It is important to determine the fire test days at which detachment appear. If they happen during the shortening stage when the column is approaching failure, such detachment would not have a significant adverse effect. But if they occur during the elongation stage, such serious failure would greatly affect the fire-resistant steel column. This will be examined by analyzing average temperature and temperature distributions in steel sections. These figures present average steel section temperatures along column length and individual steel temperature measuring location with the largest temperature differences for unloaded column specimens. Along the column length, there are some differences in average cross-section temperature. However, the differences were relatively small, suggesting that it is acceptable to assume a uniform temperature. Temperature difference in cross-section seem to be high. In most cases, it's above 10%, taking thermal stress and thermal bowing into consideration, particularly if a column is slender and subject to a high load ratio. A level of 10% temperature may have significant adverse effects on column stability. It is difficult to discern a pattern of temperature distribution due to the random nature of intumescent coating cracks. Therefore, if a non-uniform temperature distribution is considered in analyzing columns, the most unfavorable temperature distribution should be assumed. Temperature differences seem to have been studied very early during the fire test, and the same trends seem to have been maintained throughout the entire fire test. There is no evidence of the expected temperature drop. This suggests that extensive cracking and debonding instead of detachment would have been the cause of such large temperature differences. Furthermore, cracking and debonding occurred during the expansion of the loaded column before any sign of failure. For plate and unloaded column specimens, the maximum difference in steel temperature at 30 minutes of fire exposure is about 2.2% and 6.3% respectively. This suggests that unloaded specimens may be considered to have uniform temperature. This figure compares average temperature of unloaded and loaded column specimens where the maximum average temperature occurs. The unloaded and loaded column specimens had very similar section factors and the same intumescent coating data and were tested in the same furnace. Therefore, the observed large temperature differences can be attributed to the non-uniform intumescent coating behavior. According to the specifications, unloaded tests are used to calculate the effective thermal conductivity of intumescent coatings. Conducting fire tests on unloaded jackson and plate specimens is an economical method. However, in order to ensure that such results can be safely applied to loaded specimens, it is important that effective thermal conductivity results from unloaded tests are modified to incorporate the effects of cracking and bonding on intumescent coating behavior. Okay, conclusions. The failure modes of intumescent coating trial included crash, debonding, and detachment. Detachment seemed to have occurred after the fire tests. Only type 1 and type 2 crash were observed in the unloaded specimens. More serious failure were observed in the loaded column specimens. Intumescent coating failure modes affected not only average temperatures, but also temperature distributions. The temperature differences for the unloaded plate and sections were relatively small, while they were high for the loaded test specimens. The average temperatures in the unloaded steel sections were lower than those in the loaded steel columns. It is important that the effective thermal conductivity results from unloaded specimens are modified to incorporate the effects of cracking and debonding on intumescent coating behavior. That's all. Thanks a lot.